atoms are there in a can that has a mass of 16.2 grams? So this is the average mass of your good old aluminum can. So if you're drinking some type of hot beverage on a summer day, let's say Coke, you finish the beverage, but you're holding the can and you find yourself wondering, I wonder how many aluminum atoms I'm holding in my hand right now. Well, we have the tools to actually calculate approximately how many aluminum atoms you actually have in your hand. So we're gonna start with what we know. We're gonna start with the fact that you have allegedly measured the can, what its mass is, and it has a mass of 16.2 grams. Well, we're gonna go back to our flow chart, and I'm actually gonna clean this slide up a little bit. So we are currently right here. So we know that the mass is 16.2 grams. We want to figure out how many atoms there are in the can. Well, in order to do so, we must first use the molar mass to calculate the numbers of moles, and then use Avogadro's number to calculate the number of atoms. So if we know the atomic molar mass of aluminum, we can figure this out. Well, all we have to do to figure out what the atomic molar mass of aluminum is look at the periodic table. So I'm gonna write this down here. The periodic table has all atomic molar masses. Right, so again, not only are those average masses on the periodic table present in atomic mass units, if you're just looking at the mass of a single atom, they are also present in grams per mole for every substance. The same number applies. The same number works for both. Again, just because of how the scientists back who were working on this problem cleverly set up their work so that way, like, the numbers would all be self-consistent. All right, so I think I have given you enough of a head start. You know where to find the atomic molar mass. Again, just to go back to the flowchart, we know what Avogadro's number is, since this is equal to 6.022 times 10 to the 23rd. In this case, it's going to be atoms per mole. So you have your conversion factors. Try and set up the problem for yourself. How many atoms are there in this single aluminum can? And now if this is the moment when you have unpaused the video to continue the calculation all in a group, what I'm gonna do is set up both of our conversion factors again, like we've done before, in one big string, in one big calculation. So in order to get out of the unit of the gram and into the unit of the mole, we need to use our atomic molar mass. Well, on the periodic table, we can find that aluminum has an atomic molar mass of 26.98 grams per every mole. Now what this looks like, if we want to really set it up as like a conversion factor in a way that we've seen before, is we are going to keep the number with the mass because everything is per the mole. So this is going to look like 26.98 grams per every 1 mole. And so now we have something that looks a little bit more like a conversion factor that we have seen before. We just want to make sure that the conversion factor is oriented in the way that it's going to get us out of the unit that we don't want to be in anymore and get us into the unit that we do want to be in. So in order to get out of the unit that we are currently in, which is the gram, just as our conversion factors before, just like dimensional analysis before, we are going to take this molar mass, we're going to put the 26.98 grams in the denominator so that way grams cancel out. And also, just like before, we're gonna keep our chin up. We wanna keep the unit that we want to be in up on top. So our 1 mole, which is where we are trying to get into, is going to be up on top. Right, and just to reiterate, going back to our flow chart again, we have started in the mass. We wanted to get to the moles as a pit stop on the way to the number of atoms. So we currently got out of the unit of mass, specifically the unit in grams. We have gotten into the unit now of the mole. All right, so in order to get out of the mole and into the atom, which we can see on our flowchart here, we have to use Avogadro's number, which is 6.022 times 10 to the 23rd atoms per mole. All right, so just like our first conversion factor right here, we want to make sure the unit that we no longer want to be in is down below, right? We're leaving that behind. Now an Avogadro's number, which is 6.022 times 10 to the 23rd of whatever, it is per the mole, which means the 1 mole is going to be on the opposite side of the number, the 6.022 times 10 to the 23rd atoms. And again, we want the atoms up on top since this is our way of keeping our chin up. We're moving in the direction of the atom. The mole is going to go away. All right, now we have all of the conversions that we need. We have gotten out of the unit of the grams into the unit of the mole, and then out of the unit of the mole, and we can see the only unit that remains is that of the atom. So we can crunch our numbers. Our calculator, if you're working with a calculator that can handle numbers large enough, will give you the value of 3.62 times 10 to the 23rd atoms. And this is with significant figures. We started with 3 significant figures. We can see that our first conversion factor, since we know that these masses are average masses, had 4 sig figs. Avogadro's number is also a measured quantity, and we can see it presented here also has 4 sig figs. So the lesser of all of these values, where our first number again had 3, just to explicitly write that down, the lesser of all of these numbers is 3. So our final answer also is going to be presented with 3 significant figures. And now we know approximately how many atoms you are holding in your hand when you are holding an empty aluminum can. Right, the mass per aluminum can is going to vary, but the average mass is somewhere around 16.2 grams. So if you're holding this can, you are holding 3.62 times 10 to the 23rd atoms, or 362 0.00000. I'm not going to list out all the zeros, just kidding. It's a huge number though. You're holding a ton of atoms in your hand, and you don't even realize it. That's pretty cool. We have the means to calculate how many atoms you are holding in your hand, so long as you know what the material is made of.